Roll a ball from point A to point B, which path gets it there fastest? Your gut says a straight line. But a straight line is actually the slowest option of all. This single question left the world's top mathematicians stumped for 6 months. The day Newton received it, he stayed up all night to crack it. Yet the cleverest solution of all didn't come from mathematics. It came from optics. The problem was first posed by Galileo, who guessed the answer was a circular arc. He guessed wrong. He spent his whole life unable to solve it, and an answer didn't arrive until 54 years after his death. In 1696, Johann Bernoulli threw the challenge out to the world, giving everyone 6 months. Not a single person managed to answer it. But the person he was really challenging was Newton. By then, Newton was past 50, long retired from academic life, working as warden of the Royal Mint. The day he saw the problem, he grumbled angrily that he had no patience for foreigners pestering him with math puzzles. And yet the problem was simply too tempting to resist. Newton shut himself in his room and worked through the night until 4 in the morning, when he finally had the answer. Bernoulli, by contrast, had needed 2 weeks. Newton mailed in his solution anonymously. When Bernoulli saw it, he remarked that he knew at once who'd written it. Signature or not, he said, you can recognize the lion by its claw. In this duel, Newton solved the problem with the calculus he himself had invented. Assume the curve takes the form of some function. Apply conservation of energy to work out the ball's speed at any given height, then calculate the total time for the whole journey. But the truly astonishing part isn't how fast Newton solved it. It's that Bernoulli didn't touch calculus at all. He thought about light instead. Within a single medium, light always travels the shortest possible path. That's why when light bounces off the surface of a lake, the angle it comes in at always equals the angle it bounces out at. Any other route between start and end would be longer. But when light passes from one medium into another, it bends, refracts, and stops taking the shortest path. For centuries, nobody knew why. All anyone had was Snell's law, which described the behavior without explaining it. Then Pierre de Fermat realized that light isn't minimizing distance at all, it's minimizing time. He showed that Snell's law was really just a special case of this least time principle. Inspired by this, Bernoulli pictured the ball's fall as light refracting through countless stacked layers of different media. Imagine each layer of space corresponding to a different speed. As the ball moves from one layer to the next, it picks the fastest path at each step, exactly the way light does. Trace out that path of incoming and bent segments layer by layer, and what emerges is a curve called the cycloid. The same shape a pencil traces if you fix it to the rim of a wheel and roll the wheel in a straight line. Beyond being the fastest possible route downward, the cycloid has one more startling property. No matter where along the curve you release a ball, it always reaches the bottom at the same moment as any other ball released elsewhere on it. So it isn't just a brachistochrone, the curve of fastest descent, it's also a tautochrone, a curve of equal time. In 1697, submitting his solution, Bernoulli wrote with evident pride that he'd solved 2 problems with one stroke, one in mechanics, one in optics. What he didn't realize was that he'd stumbled onto something with far deeper consequences. In 1740, his student Maupertuis started asking a harder question. Why does light bother taking the fastest path at all? Why would the universe care? He introduced a new quantity he called action, mass times speed times distance. A 0.5 kilogram ball moving at 3 meters per second over 6 meters, for instance, has an action of 9. Bounce it back over the same distance, and the total action is 18. Maupertuis claimed that out of every path available to it, nature always picks the one that minimizes this quantity. The idea was attacked almost the moment he proposed it. His own friend Voltaire wrote a 32-page pamphlet tearing it apart point by point. Others accused him of plagiarism. Worse, Maupertuis himself couldn't fully justify it. Why should action be mass times speed times distance, and why should nature be obligated to minimize it? The whole thing sounded like a hunch. He died, amid ridicule and depression, without ever seeing it vindicated. Only Euler defended him, tightening the math and supplying the 2 pieces Maupertuis's version was missing: conservation of energy and the requirement that energy match across every candidate path. Less than a year after Maupertuis's death, a 24-year-old Lagrange supplied the full proof, his logic. If a path of minimum action exists, that point has to be an extremum of the function, meaning its first derivative is 0. Carry the derivation through, and you arrive at an equation. The time integral of kinetic energy minus potential energy equals 0. That's the modern form of the principle of least action, now known as Hamilton's equation. Work through the math on that equation, and it turns out to be nothing other than F equals ma. Newton's second law, the one drilled into every physics student, is fully equivalent to the principle of least action. which means this single principle explains why light reflects and refracts, why apples fall, why planets orbit the sun, why the universe looks the way it does at all. Branches of physics that once seemed to have nothing to do with each other turned out to be the same thing in disguise. At this point, you might wonder if least action and Newton's laws are equivalent, why not just use F equals ma and skip the fancy differential equation? Because force has direction, and direction gets messy fast. Take a double pendulum, two rods linked at a joint, each tugging on the other as it swings. Writing down the correct equations of motion from forces alone is brutally hard. But Lagrange's approach sidesteps all that. Plug in kinetic and potential energy, and the answer falls out with far less struggle. From Galileo's wrong guess of a circular arc, to Bernoulli's sly detour through optics to crack a mechanics problem. From Maupertuis's notion of action to Lagrange's complete proof, the whole story took nearly 100 years. And the rule that ended up unifying all of physics had been hiding the entire time inside a question about a ball rolling down a curve. When different fields collide at the edge of some unsolved problem, that's often exactly when a whole new world opens up. Maybe that's the most fascinating thing about science.